So, hello, everyone. So my name is Yann Cabanes. I'm working at Thales with Frédéric Barbaresco and also at the Institute of Mathematics of Bordeaux with Marc Arnaudon and Jérémy Bigot. On the talk today about classification in the Siegel space for vectorial autoregressive data is joint work with Frank Nielsen. So in this presentation, we will classify stationary signals of zero mean supposed to be complex autoregressive Gaussian processes. And in the first part, I will present the one-dimensional model, so the simpler one. And we will apply it to radar clutter clustering. And we will see that there is a manifold that appears, which is a product of Poincaré disk. And in the second part, I will present the multidimensional model, and we will apply it to stereo audio classification. And in this second part, there will be a product of Siegel disk who will appear in our articles, in our article with Frank Nielsen, published in GSI. We present some geometrical tools in the Siegel disk to perform the classification. So first, the one-dimensional model. So in Thales, we are building some, we are constructing some radar. And the aim of my PhD was from the radar data to be able to recognize the environment around the radar. So what we call the radar clutter is the information related to the environment, like the forest, the sea, the fields. So this is important to be able to adapt quickly a new environment, because no radars are mobile, so they should be able to adapt quickly. So now I present the radar data. So I just now focus on just a single burst. So it's just a radial axis from the radar. And in this direction, in the single direction, the radar sends a burst, which is a series of pulses. And after each pulse, the echoes are recorded by the radar. So after this pulse, the first line of the matrix is recorded. And the first complex number is related to the first cell. And then the radar sends around 10 pulses, and there are around 10 lines in this matrix. And each complex number represents its modulus represents the amplitude of the signal recorded. And its phase represents the difference of phase between the emitted signal and the received signal. So now what I will classify in my PhD is the environment. So each cell is now represented by a vector, and I will classify these vectors. So yeah, I will now classify the vectors of this matrix. And the question I ask is how to represent those vectors in a manifold in which the distance between them will represent how different is the nature of the clutter. So to do this, we do some assumptions on the signal we receive. And here we assume that the signal is stationary, zero mean, and is a complex autoregressive Gaussian process. And this has an equivalent vectorial formulation, which is that our observation vector Z in each cell is a product of a correlation matrix times a standard normal law X. So now what we would like to do is, from this observation vector, estimate the correlation matrix, and then use the right metric on the correlation matrices to classify our data. So now, related to the assumption of stationarity, we have a specific structure of the covariance matrices, or toplets, which means that each diagonal of the matrix is constant. So now we have a specific structure in our covariance matrices. And now I explain what metric do we choose to use on this set of toplets covariance matrices. So what we do is that for each observation vector X, we estimate its Toeplitz covariance matrix. And then we compute the distances using the information geometry metric between the corresponding normal laws with zero mean on those Toeplitz covariance matrices. So as you know, the information geometry metric can be used to compute distances between probability distributions. So now those are our probability distributions. This is meaningful because in our model, we assume that these vectors here are observations of these normal laws. So now we work on this field. I will skip the slide about the information geometry metric. So now, in fact, there is another representation space, which is equivalent to the space of Toeplitz covariance matrices, which is a product space with a positive real number and a product of complex unit disk. And this space on the right is related to, so the first number is the average quadratic power, and the coefficients in the complex unit disk are the coefficients of, they are called reflection coefficients, and they are related to the coefficients of the autoregressive model. And in fact, we prefer to work in the space on the right because we can transpose the metric and Toeplitz matrices on this product space. And we are lucky because the metric on the product space on the right is a product metric. And we recognize in the complex unit disk, in fact, the Poincaré metric just by instant here. And then this part is a Poincaré metric. So it's well known and it's a product metric. So it's better for us to work in this product manifold, because for computational reasons, it's better to compute to do several computations in a low dimensional space than one computation in an high dimensional space. So then what I do once I have represented my data in my manifold is that I classify them. So here, for example, I can use the Cabanes algorithm. And for me, the geomstat library that is related to the hackathon here is perfect. So what I did in my PhD is that I added my manifold in the geomstat library, and then I can use every classification algorithm in the geomstat library to classify my data. So now an example. Here there is a Thales radar in Saint-Mandrier in the south of France, and it was observing the south until here. It also sees this part. Here I just present the clustering result I have. So I use the Cabanes algorithms with 4 classes. I can see here the spatial classification, and here the classification in my product of Poincaré disk. So I have already no more time to detail, so I will skip to the second part of my presentation about stereo audio classification. So now the general problem is that I have a series of complex vectors. I still do the assumption that they are zero mean, and it's a stationary series. So again, I would like to find a metric space to compare them. What I represent the assumption. So in fact, if we represent this time series in one large vector, so everything in a column, the assumption of stationarity there is equivalent to the assumption that this large vector is still a normal distribution with zero mean and emission positive definite covariance matrix. But now this positive definite covariance matrix is block toplets. So in the one-dimensional case, I had toplets matrices, and now I have block toplets matrices. So then what I do here is, as in the first part, I will use the information geometry metric to compute the distances between the corresponding normal distributions with block toplets covariance matrices. And once again, there is an equivalent representation space in which now, so it's still a product manifold. And here, the first coefficient is Hermitian positive definite matrix, and the coefficients then are in the Siegel space. So it's a product of complex matrices space with singular values lower than 1. And it generalizes the Poincaré disk to the set of complex matrices. So now I will use this product space. And once again, we are lucky because the metric in this product space is a product metric. So it's better for us to use this product space. And what I did in my article with Frank was to write the explicit expression in the Siegel space of the Riemannian and logarithm map, because we did not find any references about this. So before my PhD, the distance on the scalar product were already known in the Siegel disk, but we didn't find anywhere the explicit expression of these applications, and they are useful for the classification. For example, to compute, to use the Cabanes algorithm. So there is a detail of this in our article. And also, in our article, we expressed the sectional curvature of the Siegel disk. And now, this is my last slide about the application on stereo audio classification. So what I did is that I tried to find stereo audio files. So there are two-dimensional real time series, and I tried to find stationary sounds. So I found on YouTube some videos about waterfalls and winds, and then I downloaded the audio files, and I divided them between a training set and a testing set, and then I plotted I represent them in my product space with a product of Siegel disk, and then I classify them using what I call the nearest centroid classifier, which can also be called minimum distance to mean, which is a supervised version of the Cabanes. Here is the confusion matrix I obtained. So thank you for your attention.
Thank you. Does anyone have a question about this talk? Yes. Please come here for the mic. Thank you.
Thank you.
Yeah.
Yeah, thank you, Yann, for your talk. I just heard the block toplets matrix, and I
Block
just wanted
toplets, yeah.
What is it exactly?
Block toplets matrices is like
block.
Block. Yeah, sorry, it's like a toplets matrix, but instead of a scalar coefficient, there are matrices.
Okay.
Yeah. I have no slides anymore. Okay.
Yeah. Okay. Thank you.
Just instead of block toplets, like a toplets matrix, but instead of scalar coefficients, matrices.
Okay. Thank you.
The blocks are not toplets matrix.
No, not in general.
Sorry.
Yeah.
Okay, so I have a question too. Does your theorem like to for the information geometry metric that you can give a product space? It works for for toplets matrix. Does it work for like in R plus for like Gaussian process in R, or is it really important to have the complex number assumption for this theorem? Do you know that or?
For real time series?
Yeah.
Like, so it does not have to be complex.
Okay.
In fact, in the stereo classification, there are real numbers.
Okay.
And in fact, the real submanifold, in fact, the real numbers in the Siegel disk, they are a submanifold on even the geodesics between 2 points with real coordinates stay in the real subset.
Okay, so it stays in
so
so
it's really exactly the same formula.
Exactly the same. Okay.
Yeah.
Okay. Thank you very much. So thank you for your talk and